In this video, we'll look more about bases and base strength and talk about the base dissociation constant and calculating the pH of a solution made from a base. Okay, so let's look at first this reaction of NH3 plus water and how we might write this. So first of all, we might look on the table and find where NH3 was. And so this is how you'd answer this question. Is it an acid or a base? Would look it up. And to find out is water an acid or a base, would have to decide what NH3 is doing in this reaction. So if we look it up on this table, we can see that NH3 appears in this A- column. So that means that it's going to act as a base. So going back, if we wanted to finish this reaction, if this is a base, this is going to be an H plus acceptor. So that would make us NH4 plus. It's going to take that H plus, and that means water has to act as the H plus donor. And so we're going to get OH minus from the water. So here we can see how NH4 is accepting that proton and how this Bronsted-Lowry base is also acting as an Arrhenius base by increasing the OH minus in solution. Generally speaking, if we're going to write a reaction with a base with water, we will write either B for base, so B plus H2O is going to equal BH plus OH minus, or you might also see us writing the conjugate base of some other acidic species to also show a base reaction. So this B and A minus sometimes get used interchangeably. The equilibrium constant expression for this then is going to be the products over the reactants. Again, we leave water out because it's just a solvent. If we were to write this using the other notation, this would just be the conjugate acid of that base times hydroxide over the concentration of the base itself. And this Kb is the base dissociation constant. So we have that table of Ka values. Do we need a table of Kb values? No, we do not. The Ka values are enough to find out, and here's an example of why. So let's look at NH3. So here's our reaction for NH3. We can have a Kb for the NH3 from this equation. If we have this reaction, so if we looked up its conjugate acid on that table, we could find a Ka for that conjugate acid. You'll note if we add these two equations together, since it's the base and its conjugate acid, those are going to cancel out on both sides of the equations, and we're left with water, OH minus, and H plus. And we know this equilibrium, that's Kw, which is 10 to the minus 14th. So the Ka and the Kb multiplied together will always equal 10 to the minus 14th in water at 25 C. So since we have this expression, we know we can find the Kb by just solving for Kb using this relationship. So Ka times the Kb will equal Kw. If we want to find the Kb, that's just going to equal Kw divided by Ka. So if we want to find that for NH3, here's our Kw and that Ka for its conjugate acid, 10 to the minus 14th, and this is from that table, and that gives us a Kb of 1.8 times 10 to the negative 5th. Okay, so let's look at an example. Here's these two species. Which of these is going to be a stronger base? So you'd solve that by looking at the acid-base table. For bases, you want to look at the A- column. And since we have this division equation, it's an inverse relationship. So a stronger base will have a smaller K value because that'll give us a larger Kb when we divide. So take a look at this table and decide whether CO3 2- or H2O is a stronger base. And the answer is CO3 2-. So going back to the table, here we see CO3 2- as a base. And here's water as a base. This is lower down in the table. It has a smaller Ka, so that means it would have a larger Ke. And again, further down on the table is going to be stronger bases. But you have to look in the base column. So don't get that confused with water down here acting as an acid. You'll also notice there's a few other species on these tables that interact that way. So there is HCO3- acting as a base. NHCO3 minus acting as an acid. If you're comparing on this chart, you can see it's fairly far down, so it's not a very strong acid, and it's kind of in the middle, so it's an okay base. Trying to decide which to use in the equation, see what your products are. If you're making OH minus, then you're acting as a base, and if you're making H plus, you'll be acting as an acid. So let's look at an example of this where we have a solution where the pH is 10.5. So we'll determine the concentration of H plus and the concentration of OH minus. So remember, the pH is the negative log of the H plus. So if we want to get from the pH to the H plus, we can do the minus of both sides and take 10 to the both sides. So 10 to the negative 10.5 is equal to the concentration of H plus. And this is going to be equal to 3.16 times 10 to the negative 11th. To calculate the concentration of OH minus, we can do the POH equals 14 minus the pH. So that will be equal to 3.5. And so if we want to solve this, remember the pH is equal to the negative log, the concentration. So we'd get the concentration of OH minus is equal to 10 to the negative 3.5. And that's going to be equal to 3.16 times 10 to the negative 14th. Let's look at calculating the pH of a strong base solution. So if we have the sodium hydroxide and it's 0.1 molar, we could try and figure out the pH. And so this is a strong base. Any soluble hydroxide salt is going to be a strong base. So this is just a stoichiometry problem. The concentration of OH minus then is just going to be the same as the concentration of NaOH. We'll have this reaction here, and it's a 1-to-1 ratio, so they have the same concentration. When we find the negative log of that concentration, we get the POH for a 0.1 molar sodium hydroxide solution, and then to find the pH, we'd do 14 minus that answer to get 13. What if we wanted to find the pH of a 0.2 molar NH3 solution? Well, this is a weak base, so this means this is an equilibrium problem. And like I said before, since it's giving this concentration, this is the initial concentration. And so now we have to plug these in to find the pH of the solution. If you go on the table and use the Ka-Kb relationship, we have the Kb is 1.8 times 10 to the negative 5th. Okay, so let's look at plugging all of this in. So we'd set up the ice table. We have our NH3, and it's acting as a base. So this will give us our NH4 plus OH minus. Our initial concentration is 0.2. We're not going to worry about water because it won't appear in the equilibrium expression. These are both 0 when we start. Here we'll have minus x, plus x, and plus x. Since we had a zeros on this side, this is going to have to increase. So this at equilibrium is 0.2 minus x, and x, and x. So we have our Kb, 1.8 times 10 to the negative 5th, is equal to our products, so x squared, over our reactants. And again, Kb is a small number, so we can use the small x approximation. So this is pretty much equal to x squared over 0.2. Putting x by itself, we get x squared is equal to 3.6 times 10 to the negative 6th. And just x on its own is equal to 1.9 times 10 to the negative 3rd. This is the concentration of OH minus from the ice table. So now we have just a few steps to get to the pH. So first we can find the POH is equal to the negative log of this OH minus, and that's going to be equal to 2.72. The pH is equal to 14 minus that number, and so that would be equal to 11.28. And if we wanted to find the concentration of H plus, that would just equal 10 to the negative 11.28, which is equal to 5.3 times 10 to the negative 12th.